Somewhere in the southern sky, a star almost identical to our own sun is hiding a secret that has taken humanity 70 years to even begin uncovering. In August 2024, a space telescope built to stare at galaxies from the dawn of time turned around and pointed at something completely different, a bright, familiar star sitting just 4 light-years from Earth. What it captured was a single point of light glowing beside that star, faint, cold, and strange. Scientists checked it, tested it, and confirmed it passed every scientific standard for a real detection. Then they looked again a few months later and it was gone. No trace, no glow, nothing but empty space where something had clearly been before. This is the story of how the most powerful telescope ever built may have just found a planet next door, and then somehow lost it again. And by the end of this video, you will understand why that disappearance might be one of the most exciting mysteries in modern astronomy. To understand why this discovery matters so much, you first need to understand what makes this particular star so special. Its name is Alpha Centauri, and it is not just another twinkle in the night sky. It is our closest stellar neighbor, the nearest sun-like star system to Earth. Close enough that if humanity ever builds a spacecraft capable of reaching another star, this is almost certainly where it would go first. For generations, scientists have asked one simple haunting question about this system. Does it have planets of its own? For decades, nobody could answer with confidence. And the strange part is, it was not because our tools were too weak. By the time researchers turned their full attention to Alpha Centauri, astronomers had already confirmed thousands of planets orbiting other stars using clever techniques, watching stars wobble under a planet's gravity, catching the tiny dimming of starlight as a world passes in front of its sun, even capturing the direct glow of young, hot planets around distant suns. Each of these methods had opened a new window onto the galaxy, revealing gas giants hugging tight orbits, rocky worlds baking under alien skies, and entire systems built nothing like our own. Nearly 6,000 confirmed exoplanets now sit in the official catalogues, proof that planets are common, almost the rule rather than the exception, scattered across the Milky Way in numbers scientists once only dreamed about. The tools worked. The problem was the target itself. Alpha Centauri breaks nearly every rule that makes planet hunting possible. Most stars where planets have been found sit hundreds or even thousands of light years away, tiny and dim in our sky, easy to study precisely because they are so faint and so far. Alpha Centauri does the opposite. At just over 4 light-years away, it is practically next door in cosmic terms, so close that light leaving that star system tonight will reach your eyes in less than 4.5 years. You would think that closeness would make everything easier, and in theory it should. A nearby object should appear bigger and brighter, and any planet circling it should be easier to spot than one circling a star 100 times farther away. But in this case, proximity became the enemy. Alpha Centauri A, the largest of the stars in this system, is one of the brightest points of light in Earth's entire night sky, outshone by only two other stars. Trying to detect a small, cold planet next to it is like trying to spot a firefly hovering beside a lighthouse. The glare simply swallows everything nearby. The difficulties do not stop there. Alpha Centauri is not a single star, it is a system of three. The brightest member, Alpha Centauri A, has a close companion called Alpha Centauri B, a nearly identical twin star that circles it every 80 years, sometimes drawing as close as 11 times the distance between Earth and the Sun. Whenever telescopes try to study one of these stars, light bleeding over from the other floods the instrument, and no coronagraph, the device engineers use to physically block starlight can block two blazing stars sitting at two different spots in the sky at the same time. Far beyond this pair sits a third, dimmer member of the family, a small red star known as Proxima Centauri. Astronomers already know Proxima has planets, at least two confirmed, and a possible third still being studied, but red dwarf stars like Proxima behave nothing like our Sun. Their planets get blasted by violent flares, and often become locked with one side forever facing their star, roasting on one half and freezing on the other. If humanity wanted to find a planet that might resemble Earth in any meaningful way, the real prize was always the twin suns at the center of the system, Alpha Centauri A and B, stars with almost the same mass, the same age, and the same warmth as our own sun. There is another obstacle hiding in plain sight, and it has to do with time itself. Alpha Centauri A is roughly 5 billion years old, about the same age as our sun. Any planets that formed alongside it would have long since cooled from the fiery heat of their birth. Young planets around younger stars still glow with leftover formation heat, making them easier to photograph directly. But a planet orbiting an old, mature star like Alpha Centauri A would be cold, dim, and radiating its faint warmth only at wavelengths far outside what most instruments are built to catch. On top of all this, the star itself refuses to sit still. Alpha Centauri has one of the fastest apparent motions of any star visible to the naked eye, drifting steadily across the sky year after year in a way that is small to a casual observer, but enormous to a telescope trying to hold perfectly steady, sub-arc second precision behind a masking device. And finally, because Alpha Centauri sits directly along the crowded band of our own galaxy, thousands of faint background stars and galaxies clutter every image, any of which could be mistaken for a genuine signal. Too bright, too close, too fast, too old, too crowded, this single star system somehow became the hardest planetary target in the entire sky, despite being the nearest one. For decades, every serious attempt to search this system for planets came back with nothing but noise, static, and disappointment. Then came a telescope that was never designed for this task in the first place. The James Webb Space Telescope was built to look backward in time, capturing the faint light of galaxies that formed billions of years ago, so far away and so dim that they appear as barely visible smudges, even to Webb's massive golden mirrors. Its instruments were tuned for extreme faintness, for catching whispers of light that had traveled for billions of years across the universe. Pointing this same delicate, hypersensitive machine at one of the brightest stars in Earth's sky sounded almost reckless, like trying to use a microscope to examine the sun. Many astronomers considered the idea impractical, even risky, worried that the intense brightness could damage instruments that cost roughly $10 billion and took more than 2 decades to design and build. The safe, conservative choice would have been to leave Alpha Centauri alone and focus only on the distant universe Webb was engineered for. But one scientist refused to accept that Alpha Centauri was simply off limits. Charles Beichmann, a veteran researcher at NASA's Jet Propulsion Laboratory, had wanted to search this system for planets long before Webb ever left Earth. He put together a team willing to attempt something that had never been tried before, using one of Webb's 4 instruments, a mid-infrared camera called MIRI, to hunt not for reflected starlight but for heat itself. The logic was elegant. Any planet sitting in the temperate zone of Alpha Centauri A, the region where liquid water could theoretically exist, would likely have a temperature somewhere between roughly -70 and -50 degrees Celsius, cold by our standards, but still warm enough to glow faintly in mid-infrared light, exactly where MIRI performs best. This approach made physical sense precisely because the star was old and its planets would have cooled long ago, ruling out the near-infrared techniques used to catch young, hot worlds elsewhere in the galaxy. MIRI carries a built-in coronagraph, a specialized mask that creates an artificial eclipse over a star's position, using destructive interference to cancel out most of the starlight, while letting fainter light from nearby objects pass through relatively untouched. Under normal conditions, for a typical, modestly bright star, this technique works beautifully and has become almost routine for Webb. Alpha Centauri obliterated every one of those normal conditions. The star moved too fast to hold steady behind the mask without constant, careful correction. Its close companion flooded the frame with extra light no single mask could block. The star itself was simply too bright for Webb's fine guidance sensors, which were never designed to lock onto something this luminous in the first place. And the crowded galactic backdrop meant any real signal could easily be mistaken for one of thousands of unrelated background objects. Faced with a target that broke every standard procedure, Beichmann's team had to invent an entirely new observing strategy from scratch. Instead of pointing Webb directly at the blinding star, which risked overwhelming its tracking systems, engineers developed a technique now known as blind offsetting. The telescope would first lock onto a nearby star of manageable brightness, a distant red giant known as Epsilon Muscae, roughly 330 light-years away, purely as a stable anchor point. From there, using extremely precise calculations, the telescope would perform a calculated blind maneuver, shifting its aim to place Alpha Centauri perfectly behind the coronagraph's mask without ever looking directly at it during the adjustment. This demanded knowing the exact position of both stars down to fractions of an arcsecond, accounting for the fact that Alpha Centauri's apparent position shifts noticeably throughout the year simply because of Earth's own orbit around the Sun. Every single observation needed freshly recalculated coordinates because numbers accurate in January would already be wrong by March. The team essentially had to build custom software just to keep chasing a moving, blinding target with pinpoint accuracy. The first real attempt happened in 2023, and it failed completely. Technical difficulties made the resulting data unusable. The coronagraph could not maintain the precision needed while compensating for the star's brightness and motion at the same time, and light from the companion star scattered everywhere across the images. It would have been an easy moment to give up, and it seemed to confirm exactly what skeptics had warned from the start, that Alpha Centauri was simply beyond reach even for Webb. Instead, the team went back, studied every failure point, rebuilt their approach, and tried again. By mid 2024, the refined method finally worked in testing, and Webb proved it could observe this once impossible target with sensitivity approaching its theoretical limits. In August 2024, the telescope carried out 3 long observation sequences aimed at Alpha Centauri A, each one lasting hours, as the coronagraph suppressed the star's blinding light while detectors quietly gathered whatever faint signals might be hiding nearby. When the raw images came back, they looked like chaos, streaks of scattered light from the companion star, rippling diffraction patterns bending around the mask, and detector noise scattered across every frame. No human eye could pick out anything meaningful from that mess directly. It took sophisticated processing, comparing the Alpha Centauri images against reference stars observed under identical conditions, then subtracting out the shared instrumental patterns layer by layer to reveal what was actually hiding underneath. And there, buried in the cleaned up data, was something real. At a distance corresponding to roughly 2 astronomical units from Alpha Centauri A, comparable to the orbital distance of Mars in our own solar system, a single faint point of light appeared, more than 10,000 times dimmer than its parent star. The team named it S1. Statistically, the odds of this signal being a random fluke were less than 1 in 10 million, a level of confidence scientists take extremely seriously. But confidence in statistics is not the same as certainty in nature, so the team spent months trying to break their own discovery, checking whether S1 might be a distant background galaxy that happened to align in the same direction, cross-referencing every known astronomical catalogue and finding no match. They checked whether it could be a passing asteroid, but its position never shifted relative to the star the way a nearby moving object would. They checked whether it could be some strange artifact created inside the instrument itself, running extensive tests where fake planetary signals were deliberately hidden inside raw data to see if their process could reliably tell real signals apart from processing errors. S1 passed every single test. Then came a detail that turned this from an exciting anomaly into something far more compelling. Back in 2019, long before Webb even launched, astronomers using a powerful ground-based telescope in Chile had caught a faint, uncertain hint of something near Alpha Centauri a candidate they called C1, sitting at roughly 1 astronomical unit from the star. That signal was never confirmed, blurred by Earth's turbulent atmosphere, and dismissed by most as an interesting but unreliable hint. 5 years later, here was Webb detecting something new in almost the same neighborhood, using a completely different instrument, a completely different observatory, and a completely different technique. If both C1 and S1 were actually glimpses of the same object caught at 2 different points along an elongated oval-shaped orbit, then 2 isolated uncertain hints suddenly connected into a single coherent story, dramatically strengthening the case that something real was genuinely orbiting out there, early estimates painted a striking picture of what this object might actually be. Its temperature sat around minus 48 degrees Celsius, and its estimated mass fell somewhere between 90 and 150 times the mass of Earth, placing it firmly in the same weight class as Saturn. This was not a scorching hot gas giant hugging close to its star. This appeared to be a cold, mature planet sitting in the outer region of the habitable zone, the theoretical band around a star where conditions could allow liquid water to exist. If confirmed, this would not just be another entry on the growing list of known exoplanets. It would be arguably the most scientifically valuable directly imaged world ever found, simply because of how close and how similar to our own solar neighborhood it sits. Given the stakes, mission scientists secured special priority observation time for urgent follow-up, and 2 more observation campaigns were scheduled for February and April 2025. If S1 were truly a planet locked in orbit around Alpha Centauri A, it should appear again, shifted to a new position consistent with orbital motion. The scientific community waited with a mix of excitement and nervous anticipation. Finding a genuine planet around a star this similar to our own sun would open the door to an entirely new kind of comparative planetary science, something no other directly imaged system could offer, simply because everything else sits too far away to study in this kind of detail. The February 2025 observation went exactly as planned from a technical standpoint. Every system aboard the telescope performed flawlessly, the delicate blind offset maneuver worked perfectly, and hours of data streamed back to Earth. Excited scientists processed it using the very same pipeline that had revealed S1 only months earlier, and they found absolutely nothing. The exact spot where S1 had blazed with overwhelming statistical confidence in August was now empty. No strong signal, no faint hint, just silence. Convinced something must have gone wrong with the processing, the team reran everything with different settings, tried alternative algorithms, and dug through the raw data directly. Every attempt produced the same unsettling result. S1 had vanished. Hopeful that this was simply an unlucky moment, the team waited for the April 2025 observation window, thinking perhaps the planet had shifted into an unfavorable position that would clear up again within 2 months. But April brought the same outcome: more empty space, more silence. Whatever Webb had captured in August 2024 refused to show itself again, even to the most powerful space telescope ever built. One researcher on the team, doctoral student Aniket Sanghi from Caltech, summed up the strange situation perfectly, calling it the case of a disappearing planet. Planets, of course, do not simply blink out of existence. They follow predictable paths shaped by gravity, and if S1 genuinely orbits Alpha Centauri A, it has to be somewhere, even if that somewhere keeps shifting position over time. So scientists laid out three possible explanations for the vanishing signal. The first, and most discouraging, was that S1 might never have been real at all, an extraordinarily rare but not impossible statistical fluke in the detector noise that happened to mimic a genuine signal so convincingly it passed every test the team could throw at it. The second possibility involved some unknown, previously uncatalogued background object drifting through the frame, coincidentally lining up with Alpha Centauri during the August observation before moving on. Researchers checked this scenario carefully against data from the Gaia spacecraft, which has mapped the positions and movements of roughly 2 billion stars across our galaxy, and against decades of archival images from other telescopes. Nothing matched. No known object could explain what had been seen. The third explanation turned out to be the most scientifically exciting, and it required understanding something subtle about how coronagraphs actually work. These instruments are not equally sensitive in every direction around a blocked star. Too close to the star, scattered light drowns out anything faint nearby. Too far away, the signal fades below what the detector can register. There is a narrow sweet spot where detection becomes possible, and that sensitivity even varies depending on the angle around the star, shaped by the physical geometry of the mask itself. A planet moving along an elliptical orbit spends part of its year drifting through this sensitive sweet spot, and part of its year hidden either too close to the glare or positioned at an angle the instrument simply cannot see well. In other words, a real planet could vanish from view completely while still following its ordinary, predictable orbit, not breaking any laws of physics, just moving somewhere temporarily invisible to current technology. To test this idea properly, the research team ran an enormous number of computer simulations, generating millions of possible orbital paths consistent with everything observed so far, then checking which of those orbits were gravitationally stable within a system as complicated as Alpha Centauri. The results were striking. More than half of all the stable orbits that fit the existing data would naturally produce exactly what happened: a strong detection in August, followed by silence in both February and April. In other words, the absence of a detection during follow up was not evidence against the planet's existence. Statistically, disappearing was actually the more likely outcome given the physics involved. The planet had not vanished into impossibility. It had simply drifted somewhere the telescope could not yet reach, and the math said that was expected all along. The orbital picture that emerged from this modeling is genuinely strange and fascinating. S1 appears to travel along a highly elongated eccentric orbit, swinging dramatically closer and farther from its star throughout each orbital cycle, likely completing one full loop, somewhere between 2 and 3 Earth years. At its closest approach, it may pass within roughly the same distance Earth sits from our Sun. At its farthest point, it swings out to nearly the distance of Mars. Compare that to Earth's own nearly perfect circular path around the Sun, or even Mercury, the most eccentric planet in our solar system, and S1's orbit still stretches noticeably further into an oval shape. When the planet swings in close to its star, it becomes buried in stellar glare, invisible to the coronagraph. When it swings back out, it briefly reappears within reach of detection. The August 2024 observation likely captured it near its farthest point, while by February it had swung inward toward its closest approach, exactly where the instrument goes effectively blind. Perhaps the strangest twist involves the planet's tilt. The two central stars of Alpha Centauri orbit each other along a well-measured, shared plane. Planets forming naturally from the leftover disk of gas and dust around young stars typically inherit that same flat orientation. But S1 appears to be tilted roughly 50 degrees away from that shared plane, a dramatic and unexpected departure from what standard planet formation theory predicts. Something unusual must have happened to knock this world so far out of alignment, perhaps a violent gravitational encounter with another planet that was later flung out of the system entirely, perhaps long-term gravitational tugging from the binary star pair, gradually warping the orbit over millions of years, or perhaps migration through leftover gas early in the system's history reshaped both its distance and its tilt at once. Despite this steep angle, Detailed stability calculations suggest the orbit remains safely bound for billions of years, because the planet never travels close enough to Alpha Centauri b for the companion star's gravity to seriously disturb it. This detection, if it holds up, challenges a long standing assumption in astronomy. Roughly half of all Sun like stars in our galaxy exist in binary or multiple star systems, and for years, computer models predicted that tight binary pairs like Alpha Centauri A and B should make planet formation extremely difficult, if not outright impossible, because gravitational interference from the companion star would tear apart the raw material planets need to form. Yet here sits a possible planet doing exactly what theory said should not happen. If planets really can form and survive in a system this gravitationally chaotic, then countless other binary systems across the galaxy, long dismissed as barren, might actually host worlds of their own, dramatically expanding the potential number of planets across the Milky Way. There is also something deeply intriguing hidden in what a Saturn sized planet sitting in a habitable zone actually implies. S1 itself could never support life. It is a gas giant with no solid surface, crushed under extreme atmospheric pressure. But giant planets in our own solar system are rarely lonely. Saturn alone hosts more than 270 known moons, including Titan, larger than the planet Mercury, wrapped in a thick atmosphere with rivers and lakes of liquid methane, and Enceladus, a small icy moon hiding a vast ocean of liquid water beneath its frozen crust, actively spraying water vapor and organic material into space through cracks near its south pole. Scientists already consider Enceladus one of the most promising places to search for life in our entire solar system, and it orbits a planet nowhere near a habitable zone. Now imagine a moon like that circling a gas giant that actually sits inside the habitable zone of a sun-like star, bathed not in the dim red light of a hostile red dwarf, but in warm, familiar, steady starlight nearly identical to what falls on Earth. Such a moon could theoretically host liquid water on an open surface, under an open sky, with two suns tracing their slow dance overhead. Complex chemistry could unfold through the same kind of photochemical cycles that shaped the early atmosphere of our own planet, and the ingredients that first allowed life to take hold on Earth, liquid water, a steady source of energy, and enough time for chemistry to experiment, could theoretically be present all at once. It sounds like science fiction, yet it may be sitting only 4 light years away, quietly orbiting a planet we only just barely managed to photograph. Of course, none of this is confirmed yet, and the scientists behind this research have been careful to say so clearly. Both discovery papers, published in one of astronomy's most respected journals, describe S1 as a strong candidate, not a proven planet. A single observation, no matter how statistically solid, cannot definitively prove something is orbiting a star. True confirmation requires tracking the object across multiple points in its path and showing its motion genuinely matches gravitational binding to Alpha Centauri A. The papers also carefully consider other explanations, including the possibility that the signal came from a temporary cloud of dust kicked up by colliding asteroids or comet activity, since dust clouds can glow at similar temperatures and briefly mimic a planet's signature before dispersing. Scientists also considered whether S1 might actually be a brown dwarf, a strange in-between object too massive to be a planet, but too small to ignite as a true star. But mass estimates based on its brightness and heat place it well below the threshold typically used to define a brown dwarf, keeping it firmly in planetary territory for now. If S1 does turn out to be real, it would not just be one interesting discovery among many. It would break several records at once. It would become the closest known exoplanet sitting inside the temperate zone of a sun-like star. It would become the nearest planet ever directly imaged by an enormous margin, since almost every other directly photographed exoplanet orbits a star many times farther away. It would become the oldest directly imaged planet by far, orbiting a star roughly 5 billion years old rather than the young, newly formed systems where most direct imaging currently succeeds. And it would become the coldest world ever captured this way, proving that even mature cooled-down planets around aging stars can be photographed directly, opening up an entirely new category of worlds that had previously been invisible to this technique. Based on the orbital models built from the data collected so far, researchers have made a specific prediction. If S1 truly exists and follows the orbital path the simulations suggest, it should swing back into a detectable position sometime around August 2026. If Webb points at Alpha Centauri A again during that window and captures the object exactly where the models say it should be, that would essentially settle the question. A third detection, lining up with both the earlier ground-based hint from 2019 and the space-based detection from 2024, would make an overwhelming case that something real and gravitationally bound truly orbits our nearest sun-like neighbor. From there, Scientists could begin studying its atmosphere, tracking seasonal changes, refining its orbit with precision, and eventually searching for the moons that a system this close and this well studied might actually allow us to find. And if the August 2026 observation turns up empty again, despite favorable predicted conditions, that would not be a dead end either. It would simply mean the planet follows a path slightly different from current models, prompting scientists to refine their calculations and try again, each attempt teaching them more about how to search successfully. Whatever the ultimate answer turns out to be, something important has already changed. The techniques built specifically to survive Alpha Centauri's chaos, the blind offsetting, the reference star subtraction, the custom data processing built to fight through extreme brightness and binary contamination, do not have to stay locked to this one star system. They can now be pointed at other nearby stars that were previously considered too difficult to study this way. Tau Ceti, sitting about 12 light years out, already shows hints of possible planets. Epsilon Eridani, roughly 10.5 light years away, has a debris disk suggesting ongoing planet formation. Another tight binary pair known as 70 Ophiuchi, about 16 light years from Earth, presents a similarly challenging target where worlds might be waiting to be found using these exact same methods. For most of human history, the stars overhead were nothing more than distant points of light, subjects of myth and imagination rather than science. Then astronomy revealed that those points of light were actually distant suns. Then the search for exoplanets revealed that many of those suns host entire families of planets. And now, one difficult, painstaking observation at a time, scientists are beginning to learn the specific individual details of the worlds orbiting our very closest neighbors. No longer just statistics in a distant catalogue, but potential worlds with measurable temperatures, evolving orbits, and maybe, just maybe, moons where water could genuinely flow. The universe has always known the answer to whether a planet truly circles Alpha Centauri A. Humanity is simply building, piece by piece, mission by mission, the tools capable of finally hearing that answer across 4 light years of silence. Every failed attempt, every blind offset calculation, every reference star subtracted from noisy data has been one more step toward a moment that ancient astronomers could only imagine, actually seeing a world circling the very star our own descendants might one day travel toward. Somewhere out there right now, light carrying the truth is already traveling toward Earth, and in the coming months, that answer may finally arrive. Whatever it turns out to be, one thing is certain: the way we search for worlds beyond our own solar system will never look quite the same again. If this story pulled you in, imagine what else is waiting quietly in the corners of our galaxy, just outside the reach of our current tools. If you enjoyed this journey through our closest stellar neighborhood, hit that subscribe button so you never miss the next discovery. Drop a comment and let us know where in the world you're watching from. We love seeing just how far this curiosity travels. And if you want more deep dives into space, physics, and the biggest mysteries the universe is still hiding from us, check out more videos on this channel. The next big discovery might be closer than you think.